Alright, so we're going to do it again. So we're going to prove the Laplace transform of t squared. So I'm going to take the Laplace transform without using the table. That's the coolest part. So what we're going to do, just like in the first example, we'll say h of t is equal to t squared, h dash of t is equal to 2t. Now, in the first example, when we took the derivative of e to the 4t, we got 4e to the 4t, but e to the 4t was the exact same as e to the 4t we had up here. T is not the same as t squared. So what the heck do you do? I mean, like, this is actually a lot more different. Well, remember, by the way, what we're doing is we're trying to prove the Laplace transform of t squared. Well, now we have to prove the Laplace transform of t. And the way we're going to do that, because I can't just say, oh, the Laplace transform of t is just 1 over s squared. I can't do that because if I'm going to make the argument that I can do this without using a table, I should be able to do it for the entire process. But you're going to see in a minute that that's not entirely true. So now I'm going to prove the Laplace transform of t. Let's forget about this 2 for the moment, because t is the actual function. 2 is just a scalar. So what are we going to do? We're going to say that p of t is equal to t. So if I take the derivative, p dash of t is equal to 1. Now here's where I say that this is going to get a little more weird. So now I'm going to say, well, okay, if I'm going to be not using the table, now I need to prove the Laplace transform of 1. Now, for the sake of argument, let's just say that I don't need to do that, because the only way to do this without using, because you can't use the derivative formula here, because you take if you do another denotation of 1, you say like q of t is equal to 1, take the Laplace transform of, you take the derivative of 1, that's 0. Not much to work with there. For the sake of argument, we're going to say we know the Laplace transform of 1, because the only other way to do it without using the table is to use the actual definition, which is the improper integral from 0 to infinity of e to the minus st ft dt, where ft would be 1. Now, that would take me like another 4 minutes to do, because I have to evaluate limits at infinity and stuff like that. So we're not going to do that. So I'm going to sound like a broken record here, but we're not going to, we're going to just say that we know the Laplace transform of 1. So therefore, SPS, and P of 0 is equal to 0, because it's 0, and you plug in 0, you get 0. So SPS minus 0 is equal to 1. PS, 1 over S, sorry. I just made a huge spiel about the Laplace transform of 1 being 1 over S. Therefore, PS is equal to 1 over S squared. Now, we know the Laplace transform of t, so we can plug that in. So h dash of t is equal to 2 over S squared. So now we take the Laplace transform of both sides here. So SHS, and remember, h of t, if we plugged in 0 here, we'd get 0. So minus 0 is equal to 2 over S squared, because I've proven this, by the way, already. But let's just say we took the Laplace transform of both sides here. So SHS minus 0 is equal to 2 over S squared. Now, if I solve for HS, you're going to find that this conveniently is exactly what we wanted. And why does that work? So basically, we want to prove this without using the table, so we take the derivative. We realize, oh no, now we have a completely new function that I can't use the table, so then we try to prove that. And we realize, oh no, we have another function that we need to prove. But we made an argument that we could do that if we used the definition of Laplace. Anyway, we didn't do that. We just say that we know this. We're going to say we know this is 1 over S, which we should know. You solve for PS when you use the Laplace transform derivative formula. By the way, I haven't actually explicitly written that formula in this video, but just to if I'm going to take the Laplace transform of f to the the first derivative of the function, that's S multiplied by the Laplace transform of f minus f of 0. Where the Laplace transform of f is just going to be capital F, or Fs. So this is the formula that I've been using over and over again, where I see how I've used it here, SPS minus 0, SHS minus 0. I'm only using the first derivative Laplace transform formula in this case. But yeah, isn't it cool that this, when I took the derivative, it just so happened that when I proved the Laplace transform of t, and then take the Laplace transform formula of this derivative, that this gives me the answer. Like, it works out so well that it's just beautiful. Like, I like the way that it works out. Anyway, our final answer is equal to 2 over s cubed, which is exactly what we wanted. Thanks for watching, and I'll see you later.